Right, I'm going to give a talk today on large, minimal non-sigma scattered orders. This is joint work with James Cummings and Todd Eisworth. In some sense, this, I don't know, the chronologically sort of the center of all of this is the Jerusalem meeting last, a year ago last summer. Somehow, Todd and James had both visited me at Cornell the previous year, and we had some ideas sort of kicking around, but everything kind of came together at that meeting, and it was well, I had to pay the price of getting COVID during that meeting and dealing with the next week in a hotel in Austria, but it was still worth it. Okay, so let me I'm going to sort of to borrow a suggestion from Matt, I will avoid burying the lead and state my main theorem first, and then I will go back and give a bit of context for all of this and explain some of the terminology. So first, I guess I should say what scattered linear order is. So L is scattered if the rationals do not embed into L. And L is sigma scattered if L is just a union of Ln, where Ln is scattered. Okay, so I guess it's, what are examples of scattered orders? Well, well order is an example of a scattered order. The reverse of a well order is an example of a scattered order. You also have things like the integers there. And the sigma scattered orders also include things like the rationals. They're a typical example, though, of a sigma scattered order is you take this the subset of all x in q to the kappa such that x changes its value finitely many times. And this is sigma scattered, and in fact and somewhat counterintuitively kappa dense, right? So you might somehow think that because that being sigma scattered means that you're somehow locally countable or something like that, but far from it. This order, you might think that being kappa dense is somehow going to forbid you from being this, but no. These are, for any cardinal kappa, this is sigma scattered, and the proof of this is sort of obvious. Once you fix the number of times it changes, and you fix how much, like whether it goes up or down in between the changes, or rather the rational values in between, that sort of signature, those are scattered for, like, the things of a fixed type are scattered, and it's easy to check that. Let's see. So, and in fact, every scattered order can be built up from from nothing, from the trivial order, by taking well-ordered and conversely well-ordered sums, kind of lexicographic sums. So Laver, the sigma scattered orders are well quasi-ordered. I don't want to get into too much into what well quasi-ordered means, other than to say if you prove that a class of orders is well, or a classification problem is a well quasi-order, that is, you have some collection of objects and you have some notion of embedding. And if you prove that order is a well quasi-order, then you pretty much completely understand what the class is. It's every downwards, like every hereditary subclass, there are just finitely many obstructions to being in the class. That's what this is equivalent to what it means to be well quasi-ordered. So it's reasonable to ask, what are the smallest non-sigma scattered orders? Or what can be said about them? And what does one mean by smallest? Well, you could talk about in terms of cardinality. But you also might say, well, smallest means sort of minimal, like being non-sigma scattered, but if you take a suborder of it, which is non-sigma scattered, then the original one embeds back into it. So minimal from the point of view of this quasi-ordering. Laver already, so the history of Laver's result is that Frise had asked, are the countable linear orders well quasi-ordered? And Galvin had suggested maybe that the right context for this is really the sigma scattered orders, because this is sort of a natural, I think Frise also asked, what are the scattered orders well quasi-ordered? And Galvin isolated the notion of a sigma scattered order as being maybe the right generalization of both of those classes. And indeed, this seems like the right notion. So in some sense, the study of sigma scattered orders is sort of, set theory is there, but it's sort of ZFC set theory. It's not, there are not a lot of independence results. And okay, so the theorem is that this is Cummings. And assume square with built-in diamond at kappa, then there is a kappa plus countryman line which is minimal with respect to being non-sigma scattered. Okay, so, excuse me. I don't want to say exactly what this is, but I will make the remark that it's so about concerning this principle. One, it holds in L, and two, well, the omega version is just diamond. And three is that if kappa is singular strong limit, and square kappa fails, then there is an intermodal with measurable kappa. I think it's actually the same kappa, measurable cardinal. Let's say lambda with O of lambda equal lambda double plus. Am I remembering, James? Am I getting this part right?
Yeah, I think so.
Yeah. Okay. And this last part is really, this is a result of Asaf Renault and Ralph, I think. Anyway, there's a paper, the square with built-in diamond, or where various results are proved about this, and we actually used this, originally we're using a stronger principle. Asaf pointed out that our stronger principle is actually equivalent to this kind of more classical principle. And in one of these papers, this was sort of relayed to us kind of relatively late in the game, that right, the failure of this at all cardinals or even at a single singular strong limit gives you, the point is significant large cardinal strength, right? So the non-existence of these things has a large cardinal strength. And so in the case of kappa equals omega is already interesting. So kappa equals omega tells you that diamond implies that there's a countryman line, which is minimal with respect to being non-sigma scattered, which means that this countryman line embeds into all of its uncountable suborders, which is, answers a question of Baumgartner. And so what is, maybe we should talk a little bit about countryman lines and also natural examples of these orderings. So L is, say, kappa plus countryman. If So if L is kappa plus countryman, if its cardinality is kappa plus, and it's a union of, well, at most or exactly, it has to be exactly kappa chains. So a chain in the coordinate-wise order is one which looks like a graph of an increasing function, except you may have horizontal and vertical sections which have more than one element. These, in the case of Aleph 1, these play an important role in the sense that they're, if you would like to have a small collection of uncountable linear orders, every other one contains one of these, then countryman lines have to be on the list, because an uncountable suborder of a countryman line is again a countryman line. And these are the reason why you need at least two countryman lines on the list, because if you take a countryman line and its reverse, they have no uncountable suborders in common. There's no uncountable linear order that embeds into both, because basically if you think about what an embedding, if you look at embedding F and embedding G into L and its reverse, then if you look at the product function F cross G, its range is going to be a strictly decreasing partial function, which must intersect each of those chains in a singleton. And so kappa plus countryman lines have the property that if you look at L and its reverse, there's no order of size kappa plus that embeds into both of them. Okay, so this result, this is the first consistent example of a linear order of cardinality greater than Aleph 1, which is minimal with respect to being non-sigma scattered. The people who specialize, who enjoy the finer points of grammar should contact me after this talk and inform me what is the right punctuation or the right hyphenation convention on non-sigma scattered. Because I think literally there should be no space or no hyphen here, but that's just weird. And my most natural inclination is to actually put a space there, but that's, I'm informed, is just wrong. So I guess the hyphen should go there, but that also looks kind of strange to me. Anyway. And so this also is the first, shows that large cardinals are needed in prior consistency results. What?
2 hyphens.
2 hyphens, okay.
Philip and I, Philip Sandor.
Okay. Okay, okay. So now I feel more confident when I do it. Okay, so that's what the next part of the talk is. So it's kind of an awkward talk because it's easy for the historical context for this talk to completely overwhelm everything else because there's a lot of kind of lead up to this. So let me kind of go back, yeah.
For this diamond with for example, does it follow from 2 to the kappa equals kappa plus or kappa?
So yeah, what the reason, yeah, okay, there's so if kappa is singular strong limit and square holds, then if square holds in cardinal arithmetic tells you that diamond could hold, then the diamond with the built-in square does hold, right? And so if it fails, it means either square fails or SCH fails, and both of those give you this.
But in case kappa regular, so this principle is a square principle, or it holds, for example, in the proof of diamond from 2 to the kappa equals kappa plus this.
It has a square. It is literally, it's square, and then you have on the square sequence, you have a diamond sequence that coheres like the square coheres. And if you sit down and you try to write down a definition of square with built-in diamond, you probably, a diamond principle that also is built around a square sequence, this is probably what you will arrive at. I think there's some, it's not quite true. There may be some choices that have to be made, but more or less it's all kind of. If you see the definition, you're like, well, that's kind of what I expected. Okay. Let me, I think the next phase of the talk is I want to kind of give some historical context to this and also like some examples, right? So easy examples of non-sigma scattered linear orders. Okay, audience participation. What's the easiest example of a non-sigma scattered linear order? The reals. Okay, so R or any uncountable suborder, right? Can you justify that? Why is this true? Well, so a useful property of sigma scattered or of scattered orders is that if you have a scattered order of regular cardinality kappa, it either contains a copy of kappa or its reverse. So if you have obviously then a sigma scattered order of cardinality kappa has the same property, and the reals contain no copy of omega 1 or its reverse. An Ehrenstein line is also in this category. And for reasons that are, well, depending on how you define it, this is really kind of a tautology. An Ehrenstein line could be defined as a linear order which has no uncountable separable and no uncountable scattered suborders. I guess the beginning of the story is maybe Baumgartner. It is consistent that there is a minimal non-sigma scattered X subset of R, right? So you take a set of reals of size aleph 1, and this is just saying it's embeddable into all of its uncountable suborders, which is really, it's a slight weakening of Baumgartner's all LF1, any two LF1 dense sets of reals are isomorphic. And Dushnik and Miller proved that under CH, no set of reals of size LF1 or no set of reals is minimal with respect to being non-sigma scattered. And also Abraham and Shalah, that PFA, even PFA for post sets of size Aleph1, implies that any Countryman line is minimal non-sigma scattered. The other side of this question, the sort of Dushnik-Miller CH side of this is more mysterious. And that's actually brings us to the present in a way. What is the CH, what is the analog of, the sort of enumeration principle analog of this? Curiously enough, Baumgartner and also I guess here you would say Daniel Sokop proved that diamond plus implies there exists a minimal Suslin line. So I'm not sure, I don't think, to my knowledge, Daniel and Baumgartner maybe never met. But what happened here is Baumgartner had a proof of this, and there was a mistake in the proof, and Daniel corrected the mistake. So the claim in Baumgartner's theorem, or in paper, is correct, but it's just the proof. There was some correction that had to be made to the proof. And then, okay, so then you might also ask, very reasonably, excuse me, what else? Is there anything that is non-sigma scattered and non-sigma scattered for different reasons than these two guys are? Of course, if you contain one of these, you're also non-sigma scattered. But are there any others? And Baumgartner so if you Lex order a ladder system indexed by a stationary set of Kof omega ordinals, then it is non-sigma scattered. Now, this example is interesting because unlike those, it can never be minimal. If you take your stationary set, this ladder system, Lex ordered, there's a way of decoding what the stationary set was just from order theoretic properties of the linear order. And so it remembers at least the stationary set up to non-stationary equivalence. And so if you take your stationary set and you split it into two stationary pieces, then the suborder gives a new uncountable, a new non-sigma scattered suborder into which the original one doesn't embed. So these can never be minimal, and it's reasonable to ask are there any minimal ones other than these? I mean, these may not be minimal in a given model of set theory, but maybe there are other, like there's a model of set theory where there's a minimal one of some completely different sort. So, yes, so these, yeah, you can show that these are quite different than Ehrenstein lines. The real types don't embed into these. Like this order can never be a real type, can never be an Ehrenstein type.
Isn't it true that any uncountable
Any uncountable suborder of one of these contains omega 1. Yeah. So these are quite, in some sense, the ladder system ordered lexicographically, not anti-lexicographic. Of course, anti-lex order also gives you an order with the same qualitative properties, except it will contain then a copy of omega 1 star. These are sort of quite close to well orders in the sense that they favor this one direction and have this refining property. So there are maybe two more bits of the history that I want to say. There's a theorem due to Tetsuya Ishu and myself, which is that PFA plus implies that any minimal non-sigma scattered order contains, or is a real type or a Countryman line. And there's even and furthermore, if X is non-sigma, or if L is non-sigma scattered, and contains no real types, maybe Countryman types, then hold on, then L contains a suborder of size aleph 1, which is non-sigma scattered, and essentially is Baumgartner's example. So this, I mean, the essentially part is kind of complicated, although later a result of Hossein and myself, Lami Ramandi and myself, is that this essentially can be removed if you say Baumgartner's example or its reverse. So what was your, yeah. And then maybe two more things to remark before we go to the present, and that is that so Hossein Lami Ramandi showed that it is consistent that there is an aleph 1 sized minimal non-sigma scattered order which is neither a real type or Ehrenstein type. And so actually his order is a dense suborder of a Kurepa line, which has no Ehrenstein suborders. And he's actually, I think, in the meantime, has proved some results about the Kurepa lines themselves, like that you sort of minimal Kurepa lines. And the other is that, I mean, somehow the natural question to ask of all of this, there's maybe too much information on the board, but it is, you might wonder, is it possible that there are no minimal non-sigma scatter orders at all? And the answer is that is possible. If there's a supercompact then there is an extension with no minimal non-sigma scattered. Okay. No, at all. In some sense, so the large cardinals have the finding, the problem of given a non-sigma scattered order, finding a suborder of size aleph 1, which is non-sigma scattered. This is a problem closely related to, but not entirely the same as stationary reflection. And so it's not surprising that large cardinals show up. But it was not until the current paper where we were actually could have able to justify that. Like there were these sort of this absurd situation where we're using these really strong hypotheses to prove results which we didn't know weren't just theorems of ZFC. But it turns out that no, the intuition of this is all correct, that you expect to need a strong hypothesis to get the statement like this, and this is the counterpoint. It's just usually you discover this sort of result first. So I have about 7 minutes, and so what I will do is that about right? 7, 8, yeah. So I'll say a few words about how this argument goes. Let's focus on the aleph 1 case, because the higher cardinal case is really just generalizing the aleph 1 case in the right way. You take, well, I guess I will say some things in generality. So kappa is the cardinal, and we're interested in constructing things of size kappa plus. This is all sequences with values in Z of length at less than kappa plus, and which with I will be vague here with order type, sort of small order type restrictions on preimages. All right, so I think you want to say the preimages have size order type at most kappa times omega or something like this. A subset T of S kappa is rho 2 coherent if its difference is in this first linear order, this set of all x in Q to the if its differences are in you look at the set of all sequences which change the value finitely many times. So if you have two, let's say you have two elements of t of the same height, you subtract them, you get another sequence of the same height. You say that sequence changes its value finitely many times. I put q here, but let's put z here because they're in z.
What is the meaning of small order type restriction?
I just say the preimages, let's just say the preimages have order type at most, less than kappa times omega. And I think I want some continuity requirements here, but this is kind of the sort of thing that you don't care about if there are fewer than 5 minutes left on the talk. So a subset of, say, T of S kappa is full if it is closed under these row 2 modifications, meaning adding a sequence in this set. So what the argument is to build, okay, so the idea is that if you take a subset of S kappa which is full and coherent and you Lex order it, then you're going to get something which is a kappa plus countryman line. And the mystery, which I'm not really going to be able to shed too much light on, is how do you arrange minimality? And you arrange minimality by diamond with the built-in square allows for the construction of T subset of this S kappa, which is full row 2 coherent, and has the property that every kappa plus sized subset, which is downwards closed, contains what we call a frozen cone. Okay, so what is a cone is simply the set of all things in the tree which are comparable with some element of the tree. And a frozen cone is if you have S and T, we have the tree order, but you can also put on elements of this S kappa, you can also put an order indexed by n, which is to say that nothing which is in the T part but not the S part has value which is less than or equal to n. The new stuff that you're adding on top has only large value. And so the frozen cone is the set of things which are either, for a fixed S, is either less than or equal to S or greater than or equal to sub n T. Or sorry, greater than or equal to sub n S. So that's a frozen cone. And what you, like, there are just kappa plus many of them, right? Kappa plus times omega, many of these. And this allows you, what this really, okay, there's this part is a bit of hand waving, but there's sort of standard arguments that allow you to reduce the problem of embedding into an arbitrary suborder of size kappa plus to ones which are a frozen cone with the Lex order. And it's easy to embed into those. Those can be embedded into by just sort of some translations and shifting around of coordinates. So in some sense, the frozen cones look enough like the original tree that you can easily embed into them. And this tells you these are the only targets you really need to worry about. The kind of coming back to the very basic stuff, like we all, well, no, not we all, but many of us in my generation learned how to construct a Suslin tree by reading Kunin's book and doing this usual diamond construction. And you might ask the question, what do you get if you try to build a Suslin, like a Suslin tree, which is obviously not going to really be a Suslin tree, of finite to one functions, right? So it can't be Suslin because there are obviously anti-chains in the tree. Or you run the construction but try to construct a special Ehrenstein tree. What do you actually get out of that? Well, you get a tree with the frozen subtree property, that every uncountable subset contains a frozen cone. Right? There's a natural way, if you have a special tree, there's a variation on this ordering which you can define. That is, there's nothing between S and T which is in an anti-chain of index less than or equal to n. Like that defines the notion of a frozen cone. And it's just saying that in that, when you construct the tree, every subtree contains a frozen cone. And so, yeah, this is what allows you to control the arbitrary suborders, which was the thing that was kind of elusive. And I think I'm pretty much out of time, and that's a good place to stop.